Yeah, so I'm going to be talking about developing machine learning for metadata standardization with HTCondor and Snakemake and Wilson. It shows on. Yeah, a little bit more center. How's this? Better? Okay. So first, I'll get it out of the way. This is a project funded by the American Family Funding Initiative Award. So Colin Dewey and Mark Craven are the PIs on this award. I'm a scientist, and then over the years we've had Jeremiah Yi, a postdoc, contributed to this, as well as grad students Abrar and Tapan. So what's our problem that we were trying to address with this? And the problem's motivated by this abundance of data in molecular biology and computational biology. So for example, the sequence read archive has been growing exponentially. This is a plot on an exponential scale. And it provides a great opportunity to do aggregate analysis of large collections of data. But it's a very diverse repository of data. And while every sample has to have metadata associated with it, every submitter can invent their own kind of key value system for the metadata, which is a problem. So here's an example of key value metadata of like from an actual sample from the SRA. And there are some problems. There are references to external sources. There are things that you need to kind of look at both the key and value to figure out what they actually mean and whether they're saying that something is true or is not true about the sample. And there are sometimes spelling errors. So just doing a search of a database is probably not going to give you all the results you want if you just want to kind of query a subset or kind of do some sort of analysis of a large number of kind of a collection of samples that different people submitted to this big repository of data. So what's the solution? It is to standardize it. So this is going to be the task that we're addressing in our research problem. So we have key value pairs that are free text, and we're going to standardize them to these terms that come from ontologies that I'll talk about in the next slide a little bit more. So, and you can already see some things getting harmonized here. So there's kind of PBMCs here are called peripheral blood mononuclear cells and the other samples. So they're two different samples. Both get standardized to the same entity with the same unique ID. So our solution here is using ontologies. For those of you who don't know, an ontology is basically a vocabulary plus relationships between entities in the vocabulary. So there are many ontologies in biology and in the sciences in general, where people come up with formally defined categories and define relationships between these categories. So this is an example of kind of a piece of an ontology where the peripheral blood mononuclear cells are kind of subcategories of larger and larger categories, going all the way up to kind of a very general category of S cell. So that's our task. Take this key value metadata that's a little fuzzy, a little bit free text, and turn it into something more formal. And it's been done before. by Colin Dewey, and Matt Bernstein is a grad student that since graduated. But specifically for the MetaSRA, using this rule-based system, which the way it operates, really the core of it is this reasoning graph where you start from a key value pair, and then you have sets of rules to generate strings that are somehow derived from the key value pair. So you take, for example, the value from here, and that becomes a node in this graph, and then you would extract different words from that string, and some of that, and eventually you'll get to strings that can be matched to terms that appear in ontologies. So that's how that system matches these key value pairs to ontologies. There's a lot I'm oversimplifying here, but the idea is that there's this text reasoning graph, and it's essentially doing some sophisticated text matching that is also domain specific. So it's specifically designed for MetaSRA samples or human cell samples in the MetaSRA, in the SRA. So we wanted to do something a little bit more general. And our approach is to throw machine learning at it, because that always works. So how do we turn it into a machine learning problem? Well, we still do some text matching, still rule-based, but we strip all the domain-specific rules out of it. So we get something much more domain agnostic that maybe casts a wider net, is a little bit more kind of inclusive in what it outputs. But eventually it gives us these candidates of, hey, I think this term might match to this ontology term, or this piece of text might match to this ontology term. And it also gives us the text reasoning kind of derivation of how it arrived at that. And then we engineer some features to kind of summarize what we think is important from these text matches. And then we can just plug it into off-the-shelf classifiers. So we literally did plug it into a bunch of scikit-learn classifiers and a couple of simple neural networks and XGBoost, and it works. So it's kind of hard to see, but the MetaSRA performance is kind of at this point in the graph. Getting to that corner would be ideal, and because classifiers spit out probabilities, we don't get 1 point of yes, no, we get a curve of that we can trade off on. We can get more recall or less precision. So these are more or less precision recall curves, but they're not quite precision recall curves because the terms are coming from an ontology. So in an ontology, you have these relationships where you could be guessing a more general term, but the ground truth might be a more specific term. So these two metrics of specific and all terms, one of them is just looking at the overlap of the whole ancestry of one versus the other. And then the other one is just looking at, okay, did the specific guesses of the machine learning classifier fall within the what is the ground truth implies. But overall, we're kind of matching and slightly improving on the MetaSRA on the SRA data, and vastly improving once we move to a slightly different data set. So this is a different repository of data. It's for proteomics experiments. The metadata looks a little different, but we can still look at it as if it were key value pairs. And even the machine learning model, so I'm just showing for the random forest, it turned out to be the best one out of the ones we tried. The machine learning models, even those that are trained just on the SRA, still perform a lot better than the rule-based system on this new data set. And then when we actually train on data that's from this new data set, we improve even further. That's so part one is good and part two is unsurprising, but that's why we wanted machine learning so that we could train and adapt to new data sets. So what did I need to do to get there? This is the workflow I am using for developing these models. So I think we had I had that diagram of kind of 4 different steps. Each of these 3 steps in the end, those can be plugged in and interchanged. So we had multiple iterations on kind of versions of the text matching pipeline. We had multiple iterations of the feature representations. We tried a bunch of different classifiers. So I ended up using Snakemake to kind of define a workflow where each rule is Snakemake. You know, the snake is obviously Python. Make is make, like the Linux command make. And the workflow has a lot of pieces of it, but the good thing is, and we saw this in other talks today, is that you can have everything be part of your workflow. So downloading the ontologies from the internet is a part of the workflow. Doing the text matching, that's another piece of the workflow. The feature generation is another piece of the workflow. Kind of all the training, testing of the classifiers, different pieces of the workflow. This diagram is just actually saying what rule is depending on another rule. It's not showing you how many of these are. So for text matching, this is a bit a kind of data dependent execution, because this turns into one job per sample in whatever data set we happen to feed to it. So this is a lot, like on the order of 1,000. Those are actually not huge data sets that we're training and testing with. And then I would have multiple experiments. So these would split up into multiple versions of these. So so we have all of these different steps, and we even have like rules that are just, you know, plugging things into Jupyter notebooks and generating reports, kind of all as part of the workflow. And Snakemake makes it easy to kind of just define your rules, and then it figures out how many times what needs to run and what depends, kind of what needs to run before what. But another thing that is quite powerful with Snakemake is that you can feed it an arbitrary kind of YAML formatted configuration file, and then it turns into the Python dictionary that you can refer to in your workflow definition. So it has these things called input functions that can actually be an arbitrary Python function that can refer to entries in this dictionary that you defined. That's the configuration file. And then these inputs functions turn into lists of files for inputs in your definitions of the actual rules. So these are kind of more or less correspond to jobs in Condor, or to tasks. And then kind of from there, it goes to workflow execution. All right, so I talked a lot about not Condor so far. It comes in with this Condor profile. Very easy to install. You basically use cookie cutter to put it somewhere in your working directory, pretty much. And then this is all you need to do to modify your Snakemake command to make it work with Condor. And then every rule launches as an individual Condor job. So that's great, and that's how we use Condor with Snakemake to to do iterative development of these models. So there are pros and cons to this approach. A pro to using Snakemake is that it's backend agnostic. You can run without Condor, it can run kind of on a local machine, it can run on other clusters or whatever. Like any good workflow manager, it avoids regenerating dependencies. It's pretty important, as we heard all day today and yesterday. I like Python syntax because I'm already programming in Python, so it's nice to not to have to learn anything else. And then input functions are very powerful. You can do pretty much some arbitrary, like data-dependent workflow things with them. That, to me, that makes, and to me, using the configuration files, which separates what I want to do from how I want to do it, makes it really easy to do iterative development, because I can kind of switch to a different version of my featureizer or of my ontologies just by changing one line in the configuration file. That's very helpful. Obviously, downsides are Snakemake is file-based, so all of this works really well on a shared file system. I don't know how hard it would be to make it run without one. It might be a lot harder. And the Snakemake process needs to stay running because it's acting as your workflow manager, which in some environments is really a no-go. So pros and cons, if I had to do it all over again from the beginning, I maybe would have tried something different. Thank you.